The story of C++ begins not with a grand corporate mandate, but with a practical problem faced by a single programmer. In the late 1970s, he was working on his PhD thesis at the University of Cambridge, which involved simulating distributed systems. For this task, he found himself using Simula, a language that offered powerful features for organization, particularly the concept of classes. These classes allowed him to structure his complex simulations in a clean and logical way. However, Simula, for all its elegance, was far too slow for the large-scale simulations he needed to run. The performance overhead made it impractical for his specific demanding requirements. On the other hand, there was a language called C. C was, and remains, incredibly fast and efficient. It provided low-level access to the machine's hardware, allowing for fine-tuned control over memory and system resources. This made it perfect for systems programming and for tasks where every clock cycle mattered. But C lacked the high-level abstractions that he had found so useful in Simula. Writing large, complex programs in C was a difficult exercise in manual organization. It was easy to get lost in a sea of functions and data structures without a clear, overarching architecture to guide the process. He was caught between two worlds, the elegant but slow world of Simula and the fast but low-level world of C. This dilemma sparked an idea. What if he could combine the best of both worlds? He envisioned a new language that would retain the speed, efficiency, and low-level power of C, but would also incorporate the powerful organizational tools of Simula, namely the concept of classes. This initial project, which he started at Bell Labs in 1979, was first named C with classes. The name was intentionally descriptive. It signaled that this was not a completely new language from scratch, but a superset of C. The primary motivation behind creating C++ was to solve a growing problem in software development managing complexity. As computer hardware became more powerful, the software being built for it grew exponentially more ambitious and, consequently, more complex. Projects involving millions of lines of code were becoming common, and traditional procedural programming languages like C were struggling to provide the necessary tools to manage such scale. Developers needed a way to organize their code into logical self-contained units that could interact with each other in well-defined ways. Without such tools, large software projects would become brittle, difficult to understand, and nearly impossible to maintain or extend over time. The goal was to provide abstractions that did not impose a performance penalty. This principle became known as the zero overhead principle. It states that what you don't use, you don't pay for. And further, what you do use, you couldn't have coded any better by hand. If a feature like virtual functions or templates was used, its implementation should be as efficient as what a skilled programmer would write in a lower-level language to achieve the same effect. This was a direct response to the slowness he had experienced with Simula. He wanted to ensure that developers would not have to choose between writing elegant code and writing fast code. They should be able to do both within the same language. Another key objective was to create a language suitable for a wide range of real-world applications, especially systems programming. This meant C++ had to be capable of doing everything C could do, including direct memory manipulation, low-level hardware interaction, and building operating system kernels or device drivers. It was not intended to be a purely academic language or one confined to a specific niche. It was designed to be a general-purpose tool for professional programmers building serious, performance-critical software. Finally, the language needed to support a smooth transition for the existing community of C programmers. By making C++ a superset of C, he ensured that this investment was not lost. A C programmer could learn C++ incrementally, starting with small features like improved type checking and gradually moving on to classes, inheritance, and templates. The evolution of C++ can be traced through a series of key milestones, beginning with its humble origins as C with classes in 1979. For the first few years, it was an internal project at Bell Labs, a tool used by a small group of developers to build experimental systems. The first major change came in 1983 when the name was changed from C with classes to C++. The ++ was a clever nod to the increment operator in C, signifying that the language was an incremental improvement upon C. The first commercial release of C++ occurred in 1985, accompanied by the publication of my book, The C++ Programming Language. This made the language available outside of Bell Labs for the first time and marked the beginning of its journey toward widespread adoption. Throughout the late 1980s, the language continued to evolve rapidly. Features like templates, which enabled generic programming, and exceptions for error handling were introduced. These additions significantly expanded the language's power, allowing developers to write more flexible and robust code. The language was growing from a niche tool into a mainstream powerhouse for software development. The 1990s were the decade of standardization. As C++'s popularity surged, multiple vendors created their own compilers, each with slight variations and extensions. This created a problem of portability. To solve this, a joint ANSI and ISO committee was formed to produce a formal international standard for the language. This monumental effort culminated in 1998 with the publication of ISO IEC 14882-1998, commonly known as C++98. Following the 1998 standard, the language entered a period of relative stability, with a minor update in 2003, C++03. The next major evolution began in the late 2000s, leading to the C++11 standard. This was a massive update that modernized the language with features like lambda expressions, smart pointers for automatic memory management, and a new concurrency library. C++11 felt like a new language and revitalized the community. Since then, the Standards Committee has adopted a train model, releasing a new standard every 3 years. We have seen C++14, C++17, C++20, and C++23. Each bringing significant new features and library components, ensuring that C++ continues to evolve to meet the demands of modern software development. The impact of C++ extends far beyond the code written directly in it. Its design philosophy and syntax have profoundly influenced a generation of subsequent programming languages. Many language creators looked at C++'s success and adopted its core ideas, particularly its C-like syntax and its object-oriented model based on classes and objects. This created a family of languages that feel familiar to anyone who has worked with C++. One of the most prominent examples is Java, which was created at Sun Microsystems in the 1990s. Java's designers explicitly borrowed the syntax of C++, but aimed to simplify it by removing features they considered overly complex, such as manual memory management, operator overloading, and multiple inheritance. Another major language that owes a significant debt to C++ is C#. Developed by Microsoft as part of its .NET framework, C# also uses a syntax that is immediately recognizable to a C++ programmer. Like Java, it is a managed language that runs on a virtual machine, handling memory allocation and garbage collection automatically. Both Java and C# can be seen as attempts to take the object-oriented paradigm popularized by C++ and make it more accessible and safer for enterprise and application development, trading some of C++ low-level control for programmer productivity and robustness. The influence of C++ is not limited to large corporate-backed languages. Many scripting languages also show signs of its DNA. JavaScript, despite its name and very different execution model, adopted a curly brace syntax that is similar to C and C++. Similarly, PHP, a language that powers a huge portion of the web, began as a simple set of tools and evolved into a language with a class-based object model and syntax that clearly echoes C++. Even more recent languages, designed to solve some of the perceived shortcomings of C++, show its influence. Go, developed at Google, uses a similar procedural style with curly braces, but simplifies things by omitting classes and inheritance in favor of interfaces and composition. Rust, developed by Mozilla, is perhaps the most direct spiritual successor. While newer languages often dominate the headlines, C++ remains the invisible foundation upon which much of our modern digital world is built. Its combination of high-level abstraction and low-level control makes it the ideal choice for software that requires maximum performance and direct hardware access. This is most evident in the world of operating systems. Major parts of Microsoft Windows, Apple's macOS, and various Linux distributions are written in C++. These systems manage your computer's resources from memory and CPU cycles to files and network connections. The video game industry is another domain where C++ reigns supreme. Modern games are incredibly complex simulations with stunning graphics, realistic physics, and sophisticated artificial intelligence. To render these immersive worlds in real time requires pushing computer hardware to its absolute limits. Game engines like Unreal Engine and Unity, whose core is written in C++, are built to do just that. C++ allows developers to manage memory precisely, optimize critical code paths, and communicate directly with the graphics processing unit, or GPU. For AAA game development, where performance is the ultimate measure of success, C++ is not just a choice. It is a necessity. Beyond operating systems and games, C++ is the workhorse behind a vast array of high-performance applications. The web browser you are likely using to read this, whether it's Chrome, Firefox, or Safari, has its rendering engine written in C++. These engines are responsible for parsing HTML, CSS, and JavaScript and painting the pixels on your screen, a task that must be done with blistering speed. Similarly, many desktop applications, from Adobe's creative suite of products like Photoshop and Premiere Pro to complex 3D modeling software like Autodesk Maya, rely on C++ for their core functionality. Furthermore, C++ is critical in the world of finance, embedded systems, and scientific computing. High-frequency trading systems, where microseconds can mean the difference between profit and loss, are almost exclusively written in C++. In the embedded world, C++ runs on the microcontrollers inside your car, your medical devices, and the flight control systems of aircraft. It is used to analyze massive datasets at CERN's Large Hadron Collider and to power the databases and search infrastructure at companies like Google and Meta. In today's polyglot programming landscape, languages rarely exist in isolation. C++ plays a crucial role not just as a standalone language, but as a foundational technology that enables and enhances many newer, higher-level languages. A prime example is its relationship with Python. Python is celebrated for its simplicity and rapid development speed, making it a favorite for data science, machine learning, and scripting. However, Python is an interpreted language, which means it can be slow for computationally intensive tasks. To overcome this limitation, many popular Python libraries, such as NumPyPandas, TensorFlow, and PyTorch, are actually thin Python wrappers around highly optimized C++ code. This symbiotic relationship allows developers to have the best of both worlds. A similar dynamic exists with JavaScript, particularly in the context of web browsers and Node.js. The V8 JavaScript engine, which powers both Google Chrome and Node.js, is itself a complex and highly optimized C++ application. Its job is to take JavaScript code and compile it into native machine code on the fly, executing it with incredible speed. When you run a JavaScript application, you are actually running a sophisticated C++ program that interprets and executes your code. This allows web applications to be far more powerful and responsive than would be possible with a simple interpreter. The relationship with a newer systems language like Rust is different. It is more of a dialogue than a direct dependency. Rust was designed to address what its creators saw as a fundamental weakness in C++, memory safety. However, the C++ ecosystem is vast, and it is impractical to rewrite trillions of lines of existing C++ code. Therefore, ensuring interoperability between Rust and C++ is a major focus for both communities. Tools and libraries are being actively developed to make it easier to call C++ code from Rust and vice versa. This allows teams to write new safety-critical components in Rust while still linking against and leveraging their massive existing C++ codebases, enabling a gradual and pragmatic migration where it makes sense. Looking toward the future, the question of C++ relevance is often raised. In a world with a constant stream of new and specialized languages, will a language designed in the 1980s remain important? The answer, I believe, is a resounding yes. The fundamental trade-offs in language design have not changed. There will always be a need for a language that provides zero overhead abstraction and direct, low-level control over hardware. As long as we want to push the boundaries of performance in gaming, scientific computing, operating systems, and countless other domains, there will be a place for C++. Its future is not one of replacement, but one of continued evolution and adaptation. The C++ Standards Committee is committed to this process of continuous improvement. The train model of releasing a new standard every 3 years ensures that the language does not stagnate. The committee actively works to incorporate modern programming paradigms and to make the language safer and easier to use without sacrificing its core principles. For example, recent standards have introduced features that simplify resource management, like smart pointers, improve concurrency with threads, futures, and atomics, and add powerful functional programming constructs such as lambda expressions. One of the most significant areas of future development is making C++ safer. For decades, the language has been criticized for issues like manual memory management, which can lead to bugs like buffer overflows and dangling pointers. The community is actively exploring ways to address this. Ultimately, the future of C++ is secure because of its massive, irreplaceable foundation of code and its dedicated community. Trillions of lines of high-performance, mission-critical C++ code power the global economy and infrastructure. This code will not be rewritten overnight. Instead, it will be maintained, modernized, and extended using the evolving features of the language. No language is without its flaws, and C++ is certainly no exception. Over its long history, it has faced its share of valid criticisms, many of which stem from the very design choices that make it so powerful. One of the most frequently cited challenges is its complexity. C++ is a huge language with a vast feature set accumulated over several decades. For a newcomer, the learning curve can be incredibly steep. Mastering its nuances, from template metaprogramming to object lifetime and move semantics, requires a significant investment of time and effort. Another significant criticism revolves around memory safety. C++'s heritage gives programmers direct control over memory through pointers and manual allocation. While this control is essential for performance, it is also a notorious source of bugs. Errors like buffer overflows, use after free, and memory leaks have been responsible for countless security vulnerabilities and system crashes over the years. The compilation model is also a source of frustration. C++'s reliance on header files can lead to very long compile times, especially in large projects. Every time a header file is changed, every source file that includes it must be recompiled, leading to a cascade of work for the compiler. Finally, C++ is criticized for its kitchen sink approach, where new features are added without removing old ones. This is a consequence of backward compatibility. While this commitment is a strength, it means the language carries historical baggage. A new programmer must learn the modern way and the older, error-prone idioms they'll encounter in legacy code. This creates a confusing experience, where multiple ways exist to accomplish the same task, not all of them equally good. In reflecting on the journey of C++, from its simple beginnings as C with classes to its current status as a global standard, its endurance is what stands out most. It was born from a simple, practical need to manage the complexity of large systems without giving up the performance that is essential for demanding, real-world work. That fundamental problem has not gone away. In fact, as our software systems have grown ever larger and more interconnected, the need for tools that can handle complexity efficiently has only intensified. C++ has survived and thrived because it addresses this core challenge directly, providing a unique and powerful balance of abstraction and control. The legacy of C++ is twofold. First, there is the direct legacy of the code itself. The operating systems, the game engines, the browsers, the databases, and the scientific instruments that form the bedrock of our technological society. This vast infrastructure, built over decades by millions of programmers, ensures that C++ will remain relevant for many years to come. The second part of its legacy is its influence on the broader art of programming. C++ helped popularize object-oriented programming on a massive scale and served as the syntactic and conceptual blueprint for countless other languages. It established the idea that high-level abstraction and high performance did not have to be mutually exclusive. The path forward for C++ is one of careful, continuous evolution. It will likely never be the easiest language to learn or the trendiest language of the moment. Its role is not to be a language for all possible tasks, but to be the best possible language for the most demanding tasks. It will continue to adapt, incorporating new ideas to become safer and more expressive, while never abandoning its fundamental promise of zero overhead performance. For those of us who build the foundational systems that others rely upon, C++ remains what it has always been, an essential tool for writing efficient, elegant, and effective code. Its story is far from over.